The Auerbach-Kotlikoff model, Economic Model and Computation, Part 1. Hello and welcome to this tutorial on the Auerbach-Kotlikoff model on a 60-period overlapping generations model. This is part of a graduate course on social security and dynamic general equilibrium. And so far we have considered the effect of social security in a 2-period overlapping generation model. 2 periods of equal length, 30 years for the worker and the retiree. And of course, this demography, this structure of the model is not really very realistic, and we would like to improve upon. And we can do so by introducing annual periods, by looking at, let's say, 60 periods in our particular case, 60 years of life starting at age 20 all the way up until age 79. And then people die. So we will make it very simple. We look at a model where each cohort is the same size and people die at the end of 79, at age 79, but survival is certain until this age. So let us study the age structure in a little bit more detail, and for this reason, let's look at this whiteboard, and I will move a little bit so you can watch. So let's look at the generation that is born in T, in the period T, which is a particular year, let's say the year 2020. They are born at the age 20. So the first period of life, the period T, the year 2020, they are 20 years old. And in the year 2021, they get 21. And so on in period T plus 1 up to period T plus 59. So in the year 2079, they are 79 years old, and they will die at the end of this year, at the end of the year 2079. They're celebrating New Year's Eve, but they will not make it to the next year. We also have a generation that's born in 2019, so in period T minus 1, sorry. So they are 20 years old in period 2019, 21 years old in period T in the year 2020, and so on. And they die 1 year earlier because they are 1 year older than the generation born in 2020, so they only make it up to the year 2078 when they die at age 79. And so we complement the model by introducing more and more generations so that each year a generation is born and each year a generation dies. So the old generation here is replaced by the co-generation, which is born in the year 2079. And each period, all cohorts of each age are alive. That's basically the structure, and we have to keep this in mind. Later on, for example, we want to sum up the total wealth in this economy. Well, then we sum up the wealth of the newborn, the 21-year-olds, the 22-year-olds, and so on up to the age 79. And similarly, we will add up the labor supply, the aggregate labor supply in the economy, and then we add up the labor supply of all workers aged 20 through 64. So we will assume that at age 65 they will retire. So keep this structure of the economy, of the demographics, of the cohorts, of the generations in mind. Okay, so we will now proceed to the slides, which you can download from my homepage. And we consider a chapter from the book of Alfred Mausner and me on dynamic general equilibrium modeling, computational methods and applications, and we take material from the chapter 9.1. So the contents of this talk will be, I will introduce you to this large-scale overlapping generations model. I will specify the equations that describe the model and the setup of the model. We will calibrate it, which will not be a terrifically difficult task. And then we will study the computation. And in the first video, in this video here, I will show you how to use direct computation. So we look at the solution of a nonlinear equations problems, which is always preferable if you can do it. It's fast and very accurate in comparison to the method that we will consider in the next video, which is value function iteration. But value function iteration may only be appropriate, the only feasible solution, if you have too many kinds of households of workers in your model. And this may result, for example, from introduction of income uncertainty in this model. And of course, income uncertainty is a very important element of the study of pensions, because pensions have some kind of insurance element. And if some people are lucky and contribute a lot to the pension system and others are unlucky and have no savings upon which to fall, this may give a reason for the government to run a pay-as-you-go pension system or a pension system at all. So let's get in the introduction of the Auerbach-Kotlikoff model. Auerbach and Kotlikoff were the first to extend the two-period overlapping generations model of LA, Samuelson, and Diamond. So all these former economists who had basically came up with this two-period of overlapping generation model, LA, Samuelson, Diamond only studied a two-period model. So LA, who basically invented it in 1947, but was often not associated with the two-period overlapping generations model because he wrote his book Économie et Intérêt in French, so it was not widely noticed. And Samuelson and Diamond, independently, probably not knowing the work of LA, developed the two-period overlapping generations model later on. All of the three, LA, Samuelson, and Diamond, got awarded the Nobel Prize. LA, at first it was Samuelson, 1970, then it was LA, 1988, and then Diamond in 2010. So everyone got it 20 years apart. And they made so many terrific contributions in the field of economics, so they were just very well-deserved prizes for these three economists. Now, Auerbach and Kotlikoff, at the end of the 80s, extended the two-period model to a 55-period overlapping generations model. We will use 60 periods, and they suggested the age structure, the overlapping of all these cohorts, in their case 55, in our case 60 periods, in any period that we consider in the economy, and periods therefore could be identified with years. Of course, this is also very amenable to empirical research because most of our data on macroeconomy are annual data, and it's very convenient to have an annual model rather than, let's say, a model with periods of 30 years. And they used it to analyze fiscal policy, and we will study a simplified version of the original model now. In later videos, we will enrich our models and even use more sophisticated model than the first model of Auerbach and Kotlikoff, and our more sophisticated model, which, for example, includes income uncertainty. Of course, this is only feasible now and not in the 80s because we have such good computer power now, and we didn't have the computational power that we in the 80s that we have right now. Okay, and we will use two computational methods: direct computation, so where we solve a system of nonlinear equations. In fact, we will reduce it to the solution of a nonlinear equations in two or one variable, and value function iteration in the next video. So let me get to the structure of the household. We will distinguish between, and to the structure of the model, we will distinguish between households, firms, and the social security authority. We will neglect many aspects of modern economy. So for example, we do not have a government sector which redistributes largely and for example, taxes income progressively. We start with a very basic model. So in order that you learn the computation and get the ideas how to solve this model. So every year, every period, a generation of equal measure is born. Since we consider 60 generations, 60 different cohorts, this means that each cohort has size 1/60, and the total measure is normalized to 1, so our total population size, NT, is always equal to 1. And if the 70-year-old generations die, 160 of people die, this measure basically is deleted, and the next generation of measure 160 pops up the 20-year-old. The first period of life, which in real life is age 20, we will use the index 1. So S will be our time index and our age index, and the newborn have age index 1. This makes it a little easier in our summation formulas. During the first 40 years, TW, working years, working time, TW, they are workers and supply labor supply LST, so labor supply at HS in period T. Total time is normalized to 1, so that 1 minus LST is also leisure. And labor supply will be endogenous. After TW years, after 40 years, they retire. Retirement is mandatory, so there are of course also models of endogenous retirement where people choose when to retire. In our models, endogenous, and then they supply 0 labor. The leisure goes up to 1 for those aged S larger than TW. Total number of periods is equal to uppercase T. The number of retirement periods are equal to 20, TR equal to 20. So this means that the old age dependency ratio in our model is 1/2. So we have 20 cohorts of retirees. So this is 20/60. 1/3 is the measure of the retirees. We have 40/60 workers, 40 cohorts with each of measure 160. And if we sum this up, we have our measure of total workers is 2/3, the measure of total retirees is 1/3, and the ratio of these two is just 1/2. So actually, our dependency ratio, old age dependency ratio, is not so far from empirical values, which you got to know at the beginning of this lecture on pensions, a couple of videos before. Now, the household maximizes lifetime utility at the beginning of age 1 and period T. And we continue to assume that we have an additive utility over time. So we add up utility as a 20-year-old at age 21, at age 22, up to age 79. But we discount utility in old age with the factor beta. And we, for example, would choose a discount factor beta equal to 0.96, so that we have a discount rate of approximately 4% for each year in the future. CST and LST denote consumption of labor supply of the S-year-old generation at time T, and we assume a simple instantaneous utility function. In fact, we use a Cobb-Douglas function, C times 1 minus L to the power gamma to the power 1 minus sigma minus 1 over 1 minus sigma. So we got to know this utility function before. It's a Cobb-Douglas case. It's as we will see, very convenient way, very convenient instantaneous utility function, because it helps us to compute the labor supply in a very straightforward way. 1 over sigma is our intertemporal elasticity of substitution, or also sigma is also called the coefficient of relative risk aversion. We will set it to 2. And gamma is the weight of leisure in utility. We will set it to 2.0, so that our average labor supply is around 0.3, 0.35, so that we work 30% of our available time. And what's new is this constant psi here in equation 2 for the instantaneous utility function. Now we will find that this assumption is extremely convenient for one particular reason. When we compute the model with the help of value function iteration, we might have to evaluate this instantaneous utility function in our MATLAB or Gauss program for zero consumption, c equal to 0. Now, since 1 minus sigma is equal to -1, if we have c to the power -1 and c is equal to 0, our computer program breaks down. We have c to the power -1, so we are done. Basically, we have infinity, and this returns a runtime error, and our program breaks down. So in order to be able to compute utility even for zero consumption, we introduce this tiny constant psi, which we will set to 0.001. And this allows us to also solve the model with the help of value function in case, well, in our computation, consumption turns out to be equal to 0. We further assume that the individuals are born without any wealth, and they also die without any wealth. So K1 and K61 are equal to 0 in each period t. So this is A1, A61 are the asset levels at the age of 1 when we are born, and A61 is basically the asset level when we have died in the first period after death. So of course we do not leave behind wealth, and we are born without wealth. So what we assume is that there's no inheritance bequest motive in our model, so there's no parent-child structure. There are other models who consider this. And we have deterministic lifetime, so if you die, you do not die at age 59, for example, and then because you died early, you still have assets and leave it to someone. No, in our case, we have certain lifetime, and we assume no bequests. So then our real budget constraint of the worker, equation 3, looks as follows. We get wage income, WT, LT, ST. WT is our wage, real wage. We work LT hours. Tau T is our social security contribution tax. Our social security tax, tau, will be imposed only on earnings on labor income. So 1 minus tau times WL is our net labor income, our net earnings. We also have wealth AST at the beginning of period T, at the beginning of HS, and earn the interest rate RT over the period T. And at the end of the period T, we get paid the savings and the interest rate, 1 plus RT times AST. And we use this savings plus interest plus our wage income to pay for consumption, CS, and wealth at the beginning of next period, AS plus 1 in period AT plus 1. So we have a simple budget constraint that you also know from the Ramsey model. In old age, as a retiree, we do not get pension income, we do not get wage income, so we do not get net wages, but we receive pensions. And we assume pensions are lump sum and do not depend on contributions. We have considered different cases in our two-period overlapping generations model, and we will reintroduce it later. But for the time being, let's assume we get a lump sum pension in old age, so at age TW plus 1, 41 up to age 60. So the budget constraint of the retiree is described in equation 4. Then we can form the Lagrangian of the 1-year-old in period T. And this is given by this rather long expression on slide 7. So we have instantaneous utility in period t. We have instantaneous utility in period t plus 1 at h2, which we discount at the factor beta. We have instantaneous utility in period 3, which we discount t plus 1 at h3, which we discount by beta square, and so on. And in our last period, we have the utility as the 60-year-old, which we discount by beta to the power of 59. Our labor supply is equal to 0, so that leisure is equal to 1, and we consume C60 at age 60 in period t plus 59. Now, in each period, we also have a budget constraint, and the Lagrange multiplier of this budget constraint is denoted by lambda st for the s-year-old in period t, and you can simply find the budget constraints here in the rectangular brackets. So for the young households, it's net wage plus savings, and of course the 1-year-old has no savings, is allocated to next period wealth and consumption. And in old age, we do not get a labor income, but we receive a pension instead. And when we differentiate the Lagrangian function with respect to our optimal policies on consumption, labor supply, and savings, we get to the first order conditions. Equations 5 and 6 describe the first order conditions of the worker equation, and we get to the first order condition of the retiree when we consider equation 6 and set labor supply equal to 0. So equation 5 is the well-known first order condition with respect to labor. So we compare the disutility from working, which is loss in utility from leisure, which is UL, the derivative of the instantaneous utility function, the partial derivative with respect to L. And we compare our loss of utility due to working 1 extra unit and sacrificing leisure to our gain in utility. And of course, we get the net wage 1 minus tau WT for working an extra unit. And this will provide us with marginal utility UC, the partial derivative of the instantaneous utility function with respect to consumption. And of course, in equilibrium, they are equal. Otherwise, we would increase lifetime utility or even period utility if we increase or decrease labor, depending on which of the two sides of this equation is larger. And the very convenient feature of our Cobb-Douglas utility function is that we have, as a consequence, a linear function in consumption and leisure, or we can relate consumption and labor linearly to each other, which will be very convenient for the programming. Equation 6 is our first order condition with respect to savings, our well-known Euler condition. And here we compare the utility of consuming 1 extra unit today, or rather saving it, receiving interest 1 plus R, gross interest next period, which gives us utility UC of consumption next period and leisure next period, which we still have to discount by the factor beta in order to make it comparable to our utility loss in the present period t. And of course, in the optimum, we have to be indifferent between the use of an extra unit of the consumption income, either in the consumption today or consumption tomorrow. And when we substitute our Cobb-Douglas utility function in equation 16, we are left with the bottom equation here on slide 8. Now the retiree does not optimize his labor supply. His labor supply is equal to 0, so he enjoys leisure 1. But of course, he optimizes over his savings, so equation 6 is also a first order condition of the retired worker we have to set equal labor supply equal to 0 in this case. Firms are described as in the rest of the course, so we assume that there's perfect competition in goods and factor markets, so therefore the marginal product of capital and labor will be equal to the factor prices. We assume constant returns to scale, so this implies that equilibrium profits are 0. We have a Cobb-Douglas production function, so that yt is equal to k to the t to the power alpha, lt to the power 1 minus alpha. So alpha is the production elasticity of capital, and we will set it to 0.36 in our calibrated model. The firms, we assume that there are infinite number of firms of measure 1, so the profits are given by production minus labor cost minus interest rates cost, and of course the capital stock depreciates by the rate with the rate delta. We would set delta equal to 10%, and the optimization conditions here are that the wage rate is equal to the marginal product of capital, equation 8, and that the interest rate is equal to the marginal product of capital minus the depreciation rate. So marginal product of labor, marginal product of capital. Equations 8 and 9. We now introduce the Social Security Authority. We know they tax labor income at the rate tau. Total labor income is equal to WT times LT. LT is aggregate labor. And they have to finance pensions of the retired people. So we know there are 20 cohorts of retired people, and we have 60 cohorts altogether. We know that the measure is 1/3 of the cohorts, and therefore the budget is presented by equation 10. The total Social Security contributions, tau times W times L, are equal to total pension payments of the Social Security Authority. And since the measure of the retirees is 1/3, we have that it's equal to 1/3 of the pensions. So in capital market equilibrium, we have the total savings is equal to the aggregate capital stock. So we have savings AST of the S-year-old. We sum up all the savings from S equal to 1 equal to S equal to 80. These are equal to aggregate savings, and since the only asset in our economy is capital stock, total savings must also be equal to total capital stock. That's the capital market equilibrium. And we can proceed to describe the general equilibrium using the recursive representation of Stokes, Lucas, and Prescott. Therefore, we define the value of the objective function of the S-year-old agent with individual values AST as value as Vs, the function of AST. And we have the exogenous variables capital stock, aggregate capital stock KT, aggregate labor LT, and the pension PEN. Many authors, many researchers drop these aggregate variables. We will use them so to make things a little clearer, especially if we later on consider the dynamics in our economy, and the aggregate variables may change for this. So we compute the value function in the second video as a function of the individual asset AST for given capital stock, labor supply, aggregate labor supply, and pensions. And this can be described by the following dynamics per dynamic program. The value function of the S-year-old is the maximum of next period utility plus discounted next period value function. So what we will end up is that the value function is just the maximum of lifetime utility. So in each period we can divide it up into the sum of the present utility plus discounted next period value Vs plus 1. In the last period of life, of course, we know that we do not live for another period, so our optimal value function is just the utility in this period where we consume all income. And so we start with the last period, can use a recursive computation. This will be analyzed in the second video in part 2. Start on the last period, compute the value function, the last period as the instantaneous utility from consuming everything we got, all the income and all our savings plus interest, enjoying leisure of 1, and we start to initialize last period value by last period optimum utility. Then we go back 1 period at the age 59 and maximize the value at this age, and the value at this age is utility at age 59 and discounted utility from age 60, which is our value function at age 60. And we can go on like this, going back 1 year each time until we get to the value function at age 1, which is then the optimum of our lifetime utility. And we can define an equilibrium for given government policy, pensions, initial distribution of capital, AS0, as a collection of value functions, VS, individual policy rules, CS, labor S, LS, and next period savings, AS plus 1, and relative prices of labor and capital, WT and RT, such that individual and aggregate behavior are consistent. So aggregate labor is equal to the sum of the individual labor supplies of age S equal to 1, 2, 3, up to 40, our working periods. And each cohort, each working cohort has measure 1 over T, 160. The aggregate capital stock is equal to aggregate savings AT, and aggregate savings is the sum of the individual savings of all the cohorts alive in period T, and each cohort again has measure 1 over T. Relative prices WT, RT solve the firm's optimization problem by satisfying equation 8 and 9, so that the wage is equal to the marginal product of labor, the interest rate is equal to the marginal product of capital minus depreciation. Given the relative prices WT, RT, and the government policy pension, the individual policy rules solve the consumer's dynamic program 12 to 13. Now the consumer's dynamic program here, this is shown by Stokely, Prescott, and Lucas in their famous book, is given by the same solution that we derive from solving the first order conditions of the household. So there are 2 equivalent ways to solve this model. One is using the first order conditions 5 and 6, and the other one is using the value function, the dynamic program problem in equations 12 and 13. They will imply exactly the same solution in our case. And the book of Stokely Lucas with Prescott tells you when this equivalence holds. In our case, in all the models that we will consider here, this equivalence holds. So we have 2 ways to solve it, and this will be the way we apply in this video. The direct computation, we solve the nonlinear first order conditions, and the second way will be value function problem, where we solve this dynamic program as specified in equations 12 and 13. Our fourth equilibrium condition is that the goods market clears, so total production is equal to total consumption plus investment, and investment is capital stock next period minus capital stock this period and net of depreciation. And to close the model, the government budget 10, the budget of the Social Security Authority is assumed to be balanced. We calibrate this model, and I've already pointed out to you the different calibration parameters while we went along in this course, in this video. So sigma, the inverse of the intertemporal elasticity of substitution, is set equal to 2.0. So this provides a midterm empirical value that we observe and which were estimated in the empirical literature. We use a discount factor beta as we equal to 0.96 as we know it from the Ramsey model with annual periods. So take a look at the first order conditions, the Euler conditions here in equation 6. In the steady state of the Ramsey model, instantaneous utility, the marginal utility from consumption is the same in all periods. So this first factor here drops out. This need not be the case in the OLG model because we may consume different amounts of goods at HS or S+1. But let's assume again that the household would like to smooth this utility over time, meaning that the marginal utilities of consumption should be close to each other, approximately equal, and then this factor here also drops out, the first factor on the right-hand side of equation 6, and we again have that 1 over beta is equal to 1 plus the interest rate, and if we choose a real interest rate of approximately 4% annual value here in our model, this implies that beta is approximately equal to 0.96. We use a production elasticity of capital equal to 0.36. This implies that the wage share in our model is 64%, and that's in good accordance with the US. Quite recently, it has gone down a little bit, but it describes the behavior of the economy, the US economy, over the last 30, 40 years, for example. Depreciation rate of capital is 10%, and we assume a replacement ratio of pensions with respect to average net wage income, the net replacement ratio, of 30%, which you will find for the United States. And therefore, we set the pension relative to the average net wage income equal to 0.3, and the average net wage income is 1 minus tau times W, the wage rate, times the average labor supply in the economy, L bar. We choose gamma equal to 0.2, that's the weight of leisure in the Cobb-Douglas utility. So this implies that labor supply is approximately 30%, 35% on average, and we set the small constant psi equal to 0.001. So this describes all the parameters in our model, and now we just have to solve it. Let's first look at the solution that we would like to compute so that you know where we are heading. In the figure on slide 17, you see the savings age profile. So the wealth AST, which is equal to the share of the individual capital stock of the S-year-old, is 0 and when we were born at year 20, and when we are 80, we are dead, then it will be 0 again. So what we do over time is we increase our savings for old age, and then we consume our savings over the retirement period. Our working income, our net income as a worker, is higher than our pension. Our pension is just 30% of our net income. So therefore, we have little income in old age, and it makes sense to accumulate savings until our income falls, and then we consume our accumulated wealth and until age 79, and then we consume all, and our wealth, which is not shown here, drops to 0 when we are dead at age 80. So this wealth age profile is very realistic. So you also observe this kind of age profile empirically. Our age profile is hump-shaped, and after retirement, savings decline. The only thing that's different in the empirical wealth age profile, it peaks a little bit around a little earlier. And one reason for this, what might cause this, I will point out in about a couple of minutes. Let's go to the next policy function, which is labor supply at age 20 through 60 as a worker. So as you can see, on average, our labor supply is around 0.3, 0.34, 0.35, something like this. And it's falling over time. So the 20-year-olds work more than the 60-year-old in our model. Why is this the case? Well, we have an increasing wealth age profile, and there's an income effect from wealth. So richer people work less in our model. And this labor supply age profile, again, well, it's not completely realistic. So what we observe is, in reality, in real life in the United States, that labor supply is hump-shaped. So it increases with age until age 40, 45, and then it declines until age 65. One reasonable way to introduce this kind of labor age profile in our Auerbach-Kotlikoff model is to also model individual productivity, age-specific productivity. So what we observe is that the 40 and 50-year-olds are much more productive than the 20-year-old or than the 70-year-old. So what we observe is a hump-shaped age productivity profile. Workers at my age, in fact, I'm 53, are the most productive according to estimates by Hansen for the United States. There it's age 52. And it's hump-shaped, and people at age 60 are much more productive than people at age 20. Now, if you impose this productivity in the Auerbach-Kotlikoff model, and our Auerbach-Kotlikoff model here as well, then you find that the labor supply age profile is also hump-shaped and in good accordance with empirical observations, and that our capital stock also peaks prior to period 60, because people accumulate high savings when they're high productive at age 40, 50, and when the productivity goes down at age 60, 65, 70, they receive lower labor income, they're less productive, and then they already start to decumulate savings at working age, at the late working age. And we get a more realistic age profile of both capital stock and labor supply. Of course, another variable that we might consider here is health. So people sometimes have bad health shocks at age 40, especially, or 50, and then labor supply also decreases and savings decrease. Now, what does our wealth and labor supply age profiles imply for our consumption profiles? This is illustrated in the next figure here. And here we see that consumption age profile is increasing over the working age, then it drops significantly at age 60 and continues to increase until age 80. Now, this consumption age profile is not realistic. So we do not observe this huge decline at retirement age. We do observe instead a hump-shaped consumption age profile. So consumption again peaks around age 50, 55, and then declines till age 80. And we do not observe a drop at age 60. Where does this come from? Well, look at our Euler condition here at age 40. So the last working age. There we still work, let's say 0.3. And at age 41, we do not work, so L drops to 0. So this factor here is 1, this factor here is smaller than 0, and because of sigma equal to 2, the whole factor here in the denominator is larger than 1. So this implies that our consumption drops from hs to s plus 1 at hs equal to 40. Our leisure increases to 100%. Let me give you the economic intuition. Leisure increases to 100%, and in order to smooth utility intertemporally at age 60 and age 61 and 59, well, you have an increase in utility due to more leisure, 100%. So what you do in order to get the two utilities at age 59 and age 60 closer is you reduce consumption at age 60 and increase consumption at age 59 so that the two utilities are closer to each other. You smooth utility over time. And our consumption grows again at age 60 to age 61 is because, according to our Euler equation, our factor beta is smaller than 1 plus r, 1 over beta is smaller than the interest rate, 1 plus the interest rate. So we get such high returns on savings that it's beneficial, increases utility if we postpone consumption, because the increase in savings compensates for the loss due to the discounting, to the discount rate. The discount rate 1 over beta minus 1 is smaller than the interest rate, and therefore we have an increasing consumption profile over time, except for the period when we retire, when leisure goes up from 60% to 100% or 65% to 100% at age 60. So this describes the logic of our consumption age profile in the model. And now how do we get a more realistic consumption age profile in the Auerbach-Kotlikoff model? Well, one of the features that we could introduce is stochastic survival. So if in old age we have the survival probability decreases, so with a higher probability we die, this introduces a behavior that we decrease consumption over time. So rather consume now the next period, because next year we might be dead. So there we get a falling consumption profile in old age if we introduce stochastic survival. We also may get a more realistic description of the consumption age profile if we introduce endogenous retirement. So some people retire at age 57, others at 65, so that the decline is a little bit more distributed over the different age groups. And we might introduce consumption habits. So if you get used to a lot of consumption at age 55, drive a BMW. Next year, when you're 60, you will still want to drive a BMW and do not drive, let's say, a Volkswagen. And therefore, you build up habits. And just because you retire, you will not change all your habits. So let me summarize how we get our Auerbach-Kotlikoff model in better accordance with our empirical observations. The hump-shaped labor supply age profile and the hump-shaped consumption age profile without a downward jump at retirement age and a decrease of consumption in old age. We could introduce hump-shaped individual productivity profiles, which peak at age 52 in the United States, stochastic survival, endogenous retirement, or consumption habits. And in my book, Public Economics, the Macroeconomic Perspective, in question problem 6.5, you are asked to introduce some of these elements in the Auerbach-Kotlikoff and in fact show that they help to overcome the weaknesses, the deficiencies of our Auerbach-Kotlikoff model. Let us turn to the computation of the steady state, which is characterized by constant aggregates and constant individual variables. So the aggregate capital stock KT is constant and equal to K. Aggregate labor LT is equal to L. And the individual wells only depends on HS, but not on time T. So in each cohort has the wells AS and labor supply LS. And we would like to compute these profiles and the aggregate variables. Therefore, we use the following algorithm. We first provide an initial guess of the aggregate variables K and L. With the help of these variables, we can compute the factor prices W and R from the first order conditions of the firm and tau with the help of the government budget. In step 3, we get to the tricky problem of this algorithm to compute the optimal policy functions, the optimal wealth profiles and labor supply profiles and consumption profiles of the household that you just got to know here. We want to compute these profiles. That's the tricky part. Once we have computed these profiles, we just sum up the individual wealths and set it equal to the aggregate capital stock, and sum up the individual labor supply of the 1-year-old, 2-year-old, 40-year-old, and add it up to the aggregate employment L. And if the two values K and L are equal to the ones we started with in step 1, we are done. Otherwise, we have to update these variables K and L and return to step 2. And we iterate over the aggregate values K and L in the outer loop of this algorithm. And in the inner loop, we do the iteration, the computation of the individual profiles. So this is somehow a nested problem. Outer loop, aggregate capital stock, inner loop, the profiles. Now let me comment on the individual step. Step 1, initial guess of aggregate capital stock K and employment L. Now we hope that our calibration with gamma equal to 2.0 implies a working time average labor supply approximately equal to 0.3, so that we work 30% of available time. We have 40 cohorts of workers, 60 cohorts in total. Each cohort is of equal size. This implies that our measure of workers is 40 over 60, or 2/3. Multiplied by the average labor supply of 0.3 implies that aggregate labor is 0.2. And as it will turn out, that's not a bad estimate of our final solution L, actually. Next, we would like to find a guess for the aggregate capital stock. Now remember how we set the discount factor beta. We set it equal to 0.96. From the Euler equation, this implies that the real interest rate is 4%. So 1 over beta is equal to 1 plus r if the marginal utilities of consumption are equal over the different ages. And then we have this result from the Euler equation. This does not hold exactly in the final solution, but approximately. So we get a value of 4% approximately for the real interest rate. And since the real interest rate R is equal to the marginal product of capital minus depreciation, according to the first order condition of the firm, we can compute K from this equation. So we have R, alpha, L, and delta, so it's no problem to compute K, and K is going to be close to 1, so it's going to be 0.9 something. In the next step, we compute the factor prices W and R that are implied by these numbers. So we already got R. W is the marginal product of labor, so W is equal to 1 minus alpha times K to the power alpha, L to the power 1 minus alpha. And then we proceed to compute the social security tax tau that balances the budget of the pension authority. Now remember how we choose pensions in our model. We assume that pensions are constant relative to net wages. So we assume a replacement rate of pensions equal to 30%, theta equal to 30%, and theta is defined as pensions divided by 1 minus tau times W times bar L, our average labor supply. So theta measures the amount of pensions relative to average net earnings in the economy. Now, we know that in the Social Security budget, total Social Security taxes have to be equal to total pensions. Total Social Security contributions are equal to tau times W times uppercase L. So this is W times uppercase L is simply the aggregate wage income in the economy, and from this gross wage income, percentage tau is transferred to the Social Security, is levied upon the gross income as taxes. Now, what are the expenditures on pensions? So the pension is equal to theta times 1 minus tau times W times L bar. And the number of people who receive these pensions is 20 over 60, 20 cohort of retirees relative to 60 cohorts in the population. Now, noticing that the aggregate labor supply is simply the number of workers, 40 over 60, times the average labor supply times L bar, we can solve for tau from this equation, and therefore once we have K and L, we can compute W, R, and tau with the help of the two first-order conditions of the firm and the Social Security budget, asking for a replacement rate of 30%. Now comes the tricky part, step 3. And I've pointed out to you, we have two ways to compute it, the direct computation or the value function iteration. Whenever possible, use direct computation. So to get accuracy of, let's say, 10 to the power minus 6, so 0.0001 percentage changes in the accuracy of the final solution is not a difficult task using a nonlinear equation solver that relies, for example, on the Newton-Raphson algorithm. This is feasible whenever there's no income uncertainty and we only have few types of workers. So imagine we would have 100 different kinds of workers in each cohort and consider heterogeneity. Then our number of nonlinear equations, which is now 99, would of course increase by 100-fold almost when we also allow for heterogeneity. It's even worse when we allow for uncertainty, and then the number of nonlinear equations will not amount to a couple of hundreds, but to many billions of equations, and we are unable to solve it due to the curse of dimensionality. But whenever we have somehow manageable number of nonlinear equations, try to solve it directly using a Newton-Raphson algorithm or similarly to solve the nonlinear equations problems, which in our case consist of the 59 Euler equations and the 40 first-order conditions with respect to labor. If this is not possible, and we will get to know an application in chapter 6.4 of my book on public economics, where we have income uncertainty, and we show that the number of possible outcomes of different individuals amounts to a couple of billions. Well, in this case, we resort to value function iteration, and this will be considered in the next video. Now let's explain the idea of direct computation that we look at in the following. Well, we have
59 Euler equations, 40 first order conditions with respect to labor, and 60 budget constraint. We can now reduce the number of equations by substituting the budget constraint in the first order equations so that we eliminate consumption CS. So let's go back to our first order condition here. And we eliminate the consumption by replacing it with the help of the budget constraint. So as a consequence, we have eliminated 60 variables consumption and are only left with 99 variables, which are the individual wealth levels and the labor supply. So our first order condition with respect to labor then becomes equation 17. So notice we only have individual wealth level and labor supply as unknowns in this equation. W, the wage, for example, is provided in the outer loop of our computation. Similarly, the interest rate R, the steady state real interest rate, is also computed in step 2. Equation 18 is our Euler equation. So we have 99 equations, and these 99 equations are, here we have the Euler equation for the 40-year-old and for the retired person, equations 19 and 20. And we also have 99 unknowns, which are the individual wealth level, AS, and the individual labor supply, LS, for the 2 to 60-year-old and the 1 to 40-year-old. Remember that the wealth of the newborn, A1, is 0, so the newborn is born without any wealth, the 1-year-old. Now, one possibility now would be to provide an initial guess of these 99 variables and solve a nonlinear equation in these 99 variables. And we will do this in about 2 or 3 videos where we look at a large-scale economic model with several hundred variables. In the following, however, we profit from the recursive structure of the problem and transform this nonlinear equation problem in 99 variables in one nonlinear equation problem in only one variable, and that's the variable A60, the wealth level that we attain in the last period of our life when we have HS equal to 60. How can we solve this model? Well, for this reason, look at the Euler equation of the retired person who will die at age 61, and look at the person who is aged 59. What is the optimality condition of the household at age 59? His Euler equation is presented by the first equation here on slide 29. So in the nominator of this fraction here on the right-hand side, we have consumption at age 60, and therefore the whole nominator is the marginal utility from consumption in the last period of life, and we divide it by marginal utility at age 59, so which is a function of consumption at age 59, and this is provided as the expression in the brackets. Notice that we have this small constant psi here, which is equal to 0.001. R is the interest rate, beta is the discount factor, and we have 3 variables in the model. The wealth level at age 60, the wealth level at age 61 and the wealth level at age 59. We know that when we die, we do not leave bequests, so A61 is equal to 0. If we provide a guess of A60, we can compute A59 from this equation. We have A60, we have A61, we have the real interest rate and the discount factor, and we have the pension level, all provided in step 2 of the algorithm. So we can compute A59 from this nonlinear equation in just one variable. And next, we proceed and iterate backwards in time recursively and look at the Euler equation of the 58-year-old. So then we have here the 60 has to be replaced by 59, 61 by 60, 59 by 58. So if we go back in time from age 59 to 58, we again have an Euler equation in the individual wealth level A58, A59, and A60. We know A60, which was our initial guess. We know A59 from the previous computation. Now we can compute A58. And we continue like this to compute backwards in time until we have computed the level A1, the beginning of period wealth A1. One thing we of course have to consider is that once we get to the worker's age, TW, we also have to solve the labor supply condition, the first order condition with respect to labor 17 simultaneously. So for the worker, we have to solve a problem of two unknowns and two nonlinear equations, 17 and 18. And the two unknowns are the labor supply LS and the present wealth AS for given next period value of the wealth AS plus 1 and next period value of labor supply LS plus 1. And then we can go back in time and compute the implied value of the individual wealth in period at the beginning of H1, the value of the initial asset. And we know that it should be 0, but of course by choice of our variable A60 as our initial guess, the probability that this will be 0 is of course 0. And what we do next is we want to solve a nonlinear equation in this initial guess, let's call it A tilde 60, so that it implies an initial capital stock A tilde 1 that is equal to 0. So we want to solve a nonlinear equation in just one variable, the wealth level at age 60, A60, so that the implied value of the initial capital stock in the lifetime, the initial level of wealth, A1 is equal to 0. So we solve a nonlinear equation in just one variable, and to get there, we have to start in the last period, go back recursively with our Euler equation and later on with our first order condition with labor, and solve this nonlinear problem in the individual asset level over the 58 times to get to A1. Okay, so we have the outer loop over the aggregate capital stock and labor. Then comes the next loop over the individual wealth A60, and for this given level A60 we can compute the implied value of A1, and we want to solve this nonlinear equation. And during this course we have to solve the nonlinear equation problem of the household aged S with respect to the Euler equation, the optimal consumption this and next period, and if it's a worker also with respect to the optimal labor supply. how do we compute the solution to this equation here? F a tilde 60 is equal to a tilde 1 is equal to 0. So that this equation here is equal to 0. Well, we will use the so-called secant method, which is introduced in the book by Alfred Mausner and myself, Dynamic General Equilibrium Modeling, but which is also very easy to understand when we look at the following picture. So let's assume this is our first guess of A60, which in this case we call XS, and implies a first period asset level A1 at this amount, f of xs. Then we provide a second guess, xs of plus 1. It implies an initial level of wells A1 at this amount, f of xs plus 1. How do we get to the next guess of the capital stock at age 60, to the value xs plus 2? Well, we use the secant method, and this is simple geometry. So you just lay a secant through the 2 points here, f of xs plus 1, f of xs, and compute the 0 of this linear function, of this secant. And this is provided by the following formula here. So the next guess in our secant method is the previous estimate minus xs plus 1 minus xs over the difference fx of s plus 1 minus fxs. And this, of course, here you notice is just the reciprocal of an estimate of the derivative at this point here. So we just compute here the derivative at this point as a guess, and we approximate it by the slope of the secant, and this is just a Newton-Raphson algorithm in disguise here. And when we will apply this update here to compute A60, well, it's very fast. We just need 5 iterations, and the solution of the optimal wealth at age 60 will be 0.1382. Now we will implement this both in MATLAB code and Gauss code. In the MATLAB program is chapter 6 ak60.m, and the Gauss program is chapter 6 ak60.g, which you can both download from my homepage, and we will turn to the computer code next and debug it together. Let us switch into the Gauss Editor and load chapter 6 ak60.g into the editor. You will find this program together with the other programs of this graduate course on my homepage. Now, the first thing you should do when you load this computer code into the editor is to see if it works. So therefore, type the green arrow and run it. Of course, you need to notice which version of Gauss you use. So I assume that you have a more recent version, so that the commands structure, plot, control, myplot work. So this only works in more recent version of Gauss 17, 18, or 19. If you have a very old Gauss version, you need to replace these plot commands before it works. So let's run the program. And you see within a second it computes the solution to this problem. The aggregate labor supply, we use the variable name n bar here, is equal to 0.2218. So our first initial guess here, 0.20, was very close. and capital stock is equal to 0.868, also very close to our first guess. Our policy function looks like the one presented in the slides. So we have the hump-shaped capital H profile, wealth H profile. We have the consumption H profile with the king. And we have the downward sloping labor supply. Our final value of the real interest rate is 5.0%, so it's close to the 4%. Notice that our real interest rate, 5%, is larger than our discount rate, which is equal to 4%. Therefore, the consumption H profile is upward sloping, and there's only a decline as leisure is increased from around 70% to 100% at the age of retirement. Now let's get into this program and let's debug it together. It's also advisable that you always save a copy if you want to change anything, so give it a different name and save it under a different name in your directory if you want a plan to make any adjustments. So let's debug and jump through the initial lines here. So we clear the memory, we clear the screen, we introduce a small constant for the accuracy of our nonlinear equation solver, and we initialize the measurement of time for the computational time by the variable bsec. Here you find the calibration of our model in the first part. So for the discount rate, we use beta 0 equal to 0.96. Notice that the name of the variable beta 0 is different from beta because beta is reserved. It's a reserved name in Gauss for a particular function. Interest rate 4.5% initial guess, or 4%, whichever. The inverse of the intertemporal elasticity of substitution is equal to 2.0. Production elasticity of capital equal to 0.36. The replacement rate of pensions with respect to net income is equal to 30%. Depreciation rate is equal to 10%. We set the number of periods during old age, TR equal to 20, and the working time equal to 40 periods. From the balanced budget constraint of the Social Security Authority, we can compute the resulting Social Security tax, which in our case is 0.13, 13%. And we set the utility parameter gamma equal to 2. So this is the weight of leisure in utility. We also have the small constant psi equal to 0.001. Notice that we again used the variable name psi0 because psi is a reserved name by Gauss. Phi is an updating parameter. It's equal to 80%. So remember that we have an iteration, outer iteration over the aggregate capital stock and aggregate labor. And in each iteration, we update our guess with a new value. And the update is 20% and 80% of the old value. So we take a weighted average of the initial value plus the newfound value and then update accordingly. So this is a tâtonnement process, which is also described in the book by Kenneth Judd on Numerical Economics, great book. Tolerance is set to 0.001. That's a percentage deviation of the final solution of the aggregate capital stock, and as well as the tolerance for the wealth level A60 at age 60 that we use in the inner loop as an initial guess here for our nonlinear equation in one variable, where we search for the optimal path of the wealth age and labor supply age profiles of the individuals. And NQ1, we set it equal to 30 is the maximum numbers of iterations over the individual policy functions. Initial value of the aggregate capital stock, which we abbreviate here by n bar, is equal to 0.2. And this provides a guess of the initial capital stock. So the initial capital stock is 0.828. We provide initial values k old and n old, which are just used as input into our accuracy measure so that our algorithm does not break down after one iteration. So what we do is we store the old capital stock in k old, the new one in k bar, and compute the percentage deviation. And if the percentage deviation is below 0.1%, we stop. And we, of course, just choose initial values for these comparative values different from k bar so that the algorithm does not hold. We store the optimal policy function in the variables aopt, copt, and nopt. So, of course, individual wealth levels are 60 for 60 cohorts, the same for consumption, and for the labor supply nopt, we just have 40 cohorts, just the workers. Okay, now we get in the iteration over the aggregate capital stock and the policy function. So this is the outer iteration where we stop once the aggregate capital stock does not change by more than 0.1% or 0.01% actually. That's our accuracy for the aggregate capital stock. And this is stored in crit and crit 0 for the capital stock and aggregate employment respectively. And we have a maximum number of iterations of 30. It's always a good idea to introduce a maximum number of iterations. So perhaps you do, let's say you make an error in doing your computations and writing down the computer code, and you do not want to iterate until eternity because of this mistake. So it's always a good idea to have a maximum number of iterations here over this loop. So we compute step 2 now. We compute the wage rate and the interest rate from the first order conditions of the households. So W and R are given here by the households, and we compute the pension level with respect to with the help of the replacement ratio. Save k bar and n bar as our old values, k old and n old, so that we can compute the percentage deviation of these two variables over the outer iteration q. We store our optimal capital stock, our initial guess for the capital stock at age 60, our asset level at age 60, in the vector k60q in order to see how our vector k60q converges. And we store the solution k1q, our initial wealth level as it's a newborn, in the vector k1q. And we hope that this converges nicely to 0. Now in the inner loop for given wages and interest rate, we compute the solution k60q, which implies that k1q is equal to 0. Once we have computed this optimal value, we just compute the new capital stock by summing over all the individual capital stock. And of course, since every household has the same measure, each cohort has measure 160, the aggregate capital stock is also equal to the average wealth. We update the capital stock k bar by a weighted average here of k old and k new, and the same for the new labor supply, which is just mean labor, mean column nopt, times 2/3 the number of workers. And we iterate over this outer loop, the aggregate, and then aggregate capital stock and the aggregate employment until it converges. Okay, in the inner loop, we compute the optimal consumption, savings, and labor supply for given aggregate numbers of W, R, and tau. So let's get to this by jumping inside this loop. So in the first iteration, in the first two iterations, we need to provide guesses of the capital stock of the wealth level at age 60. Remember, we use the secant method, so we have to provide two initial guesses. During the first iteration, Q1 is equal to 1 and Q1 is equal to 2. We have to provide a second guess. Remember that our aggregate capital stock, our initial capital stocks that we choose, K bar is approximately 1. So in old age, you decumulate your capital, and in the very last period of your retirement, after 20 years, 19 years of retirement, you probably have not much capital stock left. So as an initial guess, why not use just 10 or 20% of the average capital stock, which is 0.8. So we use 0.1 and 0.2 as initial guesses. And as we will find out, they work fairly well. So let's start with 0.1. We store this as the optimal capital stock, optimal asset level in period at the age 60. We can then compute the optimal consumption at age 60, which is the pension, plus the savings, plus the interest rate on savings, 1 plus R times K60. And we store K60Q so that we see how nice our procedure, our second method converges. And now we go backwards and iterate over the Euler equation. So for given capital stock K60, for given asset level or capital stock K61, and when we are basically dead, we know that this value is 0. We can compute K59 from the first Euler equation, as I just have pointed out. And we do this in the nonlinear equation RFO. So this stands for residual function of the old agent. And let's get to this old agent here. Let's jump into this nonlinear equation. So we have the capital stock initial value, let's say 0.1 for asset A59. We have A60, which is the optimal capital stock in the next year, the next period. So this is again given by 0.1. And K0 is just the guess. Our guess for the capital stock at HS given HS capital stock of HS plus 1 and HS plus 2 is we simply assume the same capital stock as at HS plus 1. Okay, and now we have to distinguish between the case that we are 55 years old, so that in 2 years we are dead and the capital stock must be 0, or we have stored this capital stock in the variable AOPT if we are younger than age 59. We can compute consumption at age S and at age S plus 1. Substitute this in the Euler equation. And the Euler equation is marginal utility at age S divided by beta minus marginal utility at age S plus 1 times 1 plus R. That is our Euler condition. And the solution, of course, is computed in our procedure fix thou mn1. So this is our nonlinear equation solver. And our solution now here for the capital stock for the wealth level of the 58-year-old is 0.95. 59-year-old. The one of the 60-year-old is 0.1. This was our initial value. And the one of the 61-year-old is 0. And now we can use these values, the wealth level at age 59 and 60 to compute the wealth level at age 58 in the next iteration. So we store the optimal asset level 0.195 in our column vector AOPT. We store consumption. And now we compute the optimal capital stock at age 58. So this loop is over the ages of retirement from 1 to 20, and the next loop will be over the ages of workers from 1 to 40. So let's jump to the condition of the worker, and let's run to the cursor here where we compute the optimal labor supply and the optimal savings of the worker. Now we have two first order conditions, the Euler condition for optimal savings and the first order condition with respect to labor. So we have to provide two initial guesses. And the initial guesses are simply the optimal labor supply next period, the optimal asset next period and the optimal labor supply, which we have initialized with 0.3. So these will be the two values that we will use as initial values provide to our nonlinear equation solver fix VMN1. So you can see these are the values 1.3168 and 0.30 are the values provided to our nonlinear equation solver. And now we solve the function RF young, the residual function for the young, and the residual function for the young also contains the first order condition with respect to labor supply. So let's jump into this procedure. We have two nonlinear equations which we initialized with 0, F1 and RF2. RF1 will be the Euler equation, which you can see here. And RF2 is our optimal condition with respect to labor supply. So we have the net wage 1 minus tau times W times the marginal utility UC of C1 1 minus N0 is equal to the marginal utility from leisure. So you're indifferent between working and enjoying leisure. That's our residual function too. And of course, to get there, we have to compute the consumption at young age and at age S and at age S plus 1. And we have to compute and consider whether make a special case here for the worker at age 40. Next period consumption, of course, depends on his pension. And for workers who are younger than 40, next period consumption, of course, depends on labor income. And we have to store next period employment N1, labor supply N1 in order to compute next period earnings if we are a worker that is age 39 or less. And this will compute our optimal labor supply. So in our case here, the optimal labor supply at age 40 as a young worker is 0.37189. The optimal capital stock is 1.207. And we continue like this and iterate until we have found the capital stock at the beginning of H1, A1. So let's jump to this case here into line 144. And the optimal employment the optimal capital stock that we have found is minus 1.0985. So this is far too low. This is not equal to 0. Okay, in the next iteration, we use our second guess. So let's just jump to this case here. And now we have computed the optimal wealth at age 1 for the new starting value of A60 equal to 0.2. And in this case, our optimum value is equal to 3.013. So what we have found here for the value A60 equal to 0.1, we have found a negative value of the initial wells. For the asset level A60 equal to 0.2, we have found a positive value of our initial wells equal to 3.01. So it is clear that the optimal solution must be somewhere between 0.1 and 0.2 for A60. And we will, of course, get to this if we update our guess here. Well, let's do it together. Let's go to this line. Now we are in the third iteration, and here we have the secant method. In this line here, now we have computed A1 with a guess of A60 equal to 0.1 and A1 with a guess of A60 equal to 0.2. And this is the update formula of the secant method. Here you can see simply the inverse of the derivative that we have computed with the help of the secant. And so the next initial value here for the next value for A60 is between 0.1 and 0.2. It's 0.126. And this iteration here converges very, very quickly. So let's jump down to this line here, 155, run to it, and find out how many iterations did we use. 1, 2, 3, 4, 5, 6 iteration. So here, these are the values of A1 implied by the different starting values A60 that we considered. We started with A60 equal to 0.1. Then we used 0.2. Then we used 0.12 and so on. And as you can see, after 2, 4, 6 iterations, we have found the solution. Our accuracy is even 10 to the power minus 0 to the power 9 in the accuracy of our nonlinear equation that describes the function in the form of A1. And the argument is given by our guess A60, in which we have worked recursively back to A1. Okay, and this is basically the algorithm. We are done. We update k bar, n bar as described, and it takes, let's see how many iterations we need over the aggregate capital stock. This is given by Q. Q is equal to 13. We need 13 iterations over the aggregate capital stock. And in the last iteration over the aggregate capital stock in iteration Q equal to 13, we needed 6 iterations over the value A60 to find the optimal wealth age profile of the individual. The aggregate capital stock is equal to 0.868 and the aggregate employment is equal to 0.22. And now, of course, we use the debugger here. The time is 21 minutes, but if we do not use the debugger, but let it just run through, as you've seen, it takes just a second. And then we are done and just plot our two functions here, our labor age profiles. All right. So let's stop the debugger here. The program just plots the other two functions. So we are done with the Gauss computer program chapters 6 AK60G. And as you have seen, we used 2 iterations. In the outer loop, we used an iteration over the aggregate capital stock and used the tâtonnement process to get to the new aggregate capital stock and aggregate labor by updating it by 20% with the help of the new solution. And in the inner loop, we solved the individual optimization problem. And this was a nonlinear equations problems in just one variable, A60, the guess for the wealth level at age 60. And there we use the recursive structure of the problem to compute all the other levels, A59, A58, and so on up to A1, which must be equal to 0 because we were born without any wealth. Okay, so let me jump back into our slides and conclude with some remarks. Now you got to learn how to compute an Auerbach-Kotlikoff model. We use the recursive structure so that we can exploit the backward induction here and compute A1, the initial capital stock, with the help of A60, the capital stock at age 60. We have computed the Auerbach-Kotlikoff model, and this is of course a preferable method when you are looking to find a solution to a simple problem. When you consider more complicated problems, which we will do in the following, sometimes you might be able to use this, what we call direct computation. Just use the Newton-Raphson algorithm to compute the solution, probably in one variables, or let's say in a couple of hundred variables which characterize your equilibrium. Well, you're good advised to try to find this, and we will get to much more sophisticated methods to come up with an initial guess for, let's say, 100, 200, or 500 variables. And we will consider this in about, well, 2 or 3 videos later here, and use it to compute the Laffer curve and the fiscal sustainability of pensions. However, often this method is not applicable, not feasible, if we have uncertainty in the model, and uncertainty in the model with respect to individual income and productivity. Some people are lucky and improve their efficiency and their productivity and have a high-paying job in 5 years or in 10 years. Some people are unlucky and they will get unemployed or lose their job. And this introduces a stochastic that makes it not amenable to a solution with the help of direct computation. And we need to rely upon discretization methods. So where you compute the policy function over a whole grid or a whole interval of the individual state space, in this case, the individual wealth level. And we will get to this in the next video, which is on value function iteration.